Hey, Cosmic Explorers! Caroline here. Today I'm going to guide you through a digital simulation that models Kepler's laws of planetary motion. Scientists use models to represent complex systems, test ideas, and make predictions. Models play an important role in science because they allow us to explore things we can't directly observe or manipulate, like distant planets and massive stars. In astronomy, where everything is either too far away or too large to study up close, models help us visualize how celestial objects move and interact. When using the simulation today, approach the work like a scientist. Use the model to explore, test predictions, and better understand the rules of the universe. It's time to model the cosmos. Before we start working with the simulation, let's review. What is the shape of a planet's orbit? It's an ellipse. An ellipse has two fixed points inside it called focal points or foci, which define its shape. Imagine you wanted to draw an ellipse. If you pinned 2 points on a piece of paper and used a string looped around these points to guide your pencil, you could create an ellipse by pulling the string taut and tracing a path around the points. What would happen to the ellipse if the two focal points were moved closer together? It would change shape. By changing the distance between the foci or the length of the string, you can create ellipses in different sizes and shapes. An ellipse also has a major and minor axis. The major axis is the longest line that stretches across the ellipse. It passes through both focal points. Half of this line is called the semi-major axis. For planetary orbits, the semi-major axis represents the average distance of a planet from the Sun. Determining the length of the semi-major axis is important for calculating different aspects of planetary motion. All right, we now have the basic understanding of ellipses needed to use our digital simulation. Look for the link or suggested search terms in your guided notes and open up the simulation on your device. Once you have it open, come back and we'll get started modeling orbits. Now that you have the simulation open, let's start modeling Kepler's first law. This law describes the shape of a planet's orbit as an ellipse with the Sun at one focal point. In this section of the lab, we'll examine how a planet's distance from the Sun and its velocity play a role in creating that elliptical shape. Before you get started, let me guide you through some of the controls you'll encounter. When you first open the simulation, you'll arrive at a home screen. From here, you can navigate to explore any of Kepler's 3 laws. At this point, we're going to select First Law. Please note that there is sound in the simulation. Leave it on if you like. However, if the sound bothers you, use the speaker button on the bottom right of the simulation's interface to turn it off. The control panel for the simulation is on the right side of the screen. By checking the boxes, you can change what information is displayed. For example, if I check the box next to the word speed, then the speed of the planet will be shown. The main part of the screen shows a diagram of an object in orbit. Press the blue play button to observe the object complete its orbit. As part of the lab, you'll be asked to match orbits of planets in our solar system. Find the target orbits in a drop-down menu at the top right. To match an orbit, adjust the position of the orbiting object and the size and direction of the green velocity arrow. You'll also measure each orbit's eccentricity. Eccentricity describes how stretched or elongated an ellipse is compared to a perfect circle. The simulation automatically calculates eccentricity for you. Just check the box next to eccentricity in the control panel and look for the value given on the left side of the screen. An eccentricity of 0 represents a perfect circle, where the two foci overlap at the center. As eccentricity increases toward 1, the distance between the foci increases, and the ellipse becomes more elongated. Most planetary orbits in our solar system have low eccentricity, meaning they are almost circular. But if they're so close to being circles, why does it matter that orbits are actually ellipses? Well, understanding elliptical orbits helps space engineers send spacecraft to the right place at the right time. Even tiny differences in an orbit's shape can have a huge impact when predicting the path of an object in space. Now that you're familiar with the controls, pause the video and follow the instructions in your guided notes to explore Kepler's first law. When you're done, come back to watch the next section of the video. We know from Kepler's first law that the Sun sits at a focal point within a planet's orbit. This means the distance between a planet and the Sun changes as the planet moves. But distance isn't the only thing that changes. Based on Kepler's second law, do you remember what else varies along the orbit? The planet's speed. This applies to all orbiting objects. For example, satellites around Earth slow down as they move farther from our planet. Engineers rely on this principle to design GPS satellites, ensuring they maintain the right speeds for accurate location data. In the next part of the lab, we'll use the simulation to visualize this change in speed. You will select Second Law from either the bottom menu or home page of the simulation. You'll notice a few key differences in the interface for this second law. The orbit is now divided into sections. You can change the number of divisions and whether to display information like the area swept or time passed using the controls in the top left corner. You can also mark some key points in the orbit. In our last lesson, we learned that the point in an orbit where a planet is closest to the Sun is called perihelion. The opposite point, where an object is furthest away from the central body, is aphelion. In the simulation, you'll see the terms periapsis and apoapsis, which are general terms for these points and apply to any orbiting object, not just planets. That should give you enough information to complete the next section of today's lab. Pause the video and follow the instructions in your guided notes. When you have finished exploring Kepler's second law, come back here and continue the video. Kepler's third law reveals the relationship between a planet's distance from the Sun and its orbital period. Astronomers use this law to estimate distances, such as calculating how far an exoplanet is from its star. Why might that be useful? Well, among other reasons, it can help astronomers infer whether conditions on that exoplanet might allow for life. For the final part of our lab, you'll measure the orbital periods of some planets in our solar system. To get started, select Third Law from either the bottom menu or home page of the simulation. This part of the simulation includes a few unique controls. You can add a box to record the period of any orbit you create. You can also manipulate a graph on the left side that relates the period and length of the semi-major axis. While the simulation allows you to change the mass of the star, keep it set to our Sun since we're modeling our own solar system. It's time to work. Pause the video and follow the instructions in your guided notes. When you're done, come back for the final section of the video. You've done great work today using the model to dive deeper into Kepler's 3 laws of planetary motion. You'll have a chance to evaluate the effectiveness of the digital simulation as a scientific model during the lesson activities. It's also important to realize that Kepler's laws do not only apply to planets. They also apply to moons, comets, and other objects in the cosmos. Check out the extension activity in this lesson to examine the relationship between Kepler's laws and a wide variety of objects in the universe. Until next time, stay curious and keep asking questions.
Hey, hey.